Okay, everyone. So we're going to do a really short video here on a type of differential equation that can show up on the AP exam, but more than that, I think it's kind of cool just to look at because it's an equation most of you guys have seen in one form or another in Algebra 2 and possibly in pre-calculus, but it's the exponential growth equation. So most of you guys are familiar with the equation. I'll write it up here on the top, PERT. P to the RT, where P was an initial population. R is something, they call it a growth constant. It's not the rate of growth, it's just something called a growth constant. Really what it is it's actually the same thing as this value K in this differential equation, and we'll see how we get to that. But anyway, this is how we derive that PERT equation, starting from a differential equation and working our way backwards. So really, the exponential growth differential equation is just giving us an equation that describes when the rate of change of a population is proportional to the current population. So as you can see right here, if y is supposed to represent a population, dy dt is the rate of change of that population, well, we can see that is going to be equal to, again, some proportional constant multiplied by y. Y is the current population. Okay, so if we apply separation of variables to this, why don't you give it a shot and pause the video just so you can get some practice. Apply separation of variables to this equation right here. Okay, so if you've done that, we will get that dy over y is equal to k dt. Then if we integrate both sides, this gives us natural log of y is equal to kt plus c. So if we want to get that y out of the natural log equation, we just exponentiate both sides. So we'll get y is equal to e to the kt plus c. But remember this property about exponential functions, that e to the a times e to the b is equal to e to the a plus b. So we can actually write this y function right here as the product of two exponential functions. And the really nice thing about that is that since c is a constant, when we write this as e to the c times e to the kt, well, e is a constant too. So a constant raised to a constant, that's just another constant. So what we get is ce to the kt, and now that looks a lot like the PERT equation, although we didn't put an r and we didn't put a p. But recall that this value c, that's going to be the initial population. And then k is called the growth constant. All right, and t is obviously time. So basically this is helpful because if you ever see a differential equation that looks in this form that we have up here, where it's just proportional to what the current population is. Maybe they won't even phrase it in a population question. It could just be, hey, a differential equation of the function y is proportional to the current y value. You can always know now, you don't have to go through the process of separation of variables. You can always just be like, oh, they're talking about exponential growth, they're talking about PERT, or CE to the CE to the KT as we described it down below. So let's look at a couple problems where we could utilize this. All right. So first of all, if you look at this problem, pause the video real quick. Don't try to solve it. Just come up with, okay, at the beginning, if you just saw this problem, how would you want to solve it? Okay, so I hope that a lot of you guys have actually realized that we've solved problems just like this before when we were in our unit of the fundamental theorem of calculus. Remember that the integral of a rate of change over an interval gives the net change over that same interval. So if we're given a rate of change right here and we're given the interval t equals 0 to t equals 10 hours, if we just integrate from 0 to 10, this function r of t dt, we can do that f and I and t in our calculators. What we'll end up getting should be approximately 8647. So we could have gotten this answer. We know it's going to be D. We could have gotten it this way, but why don't you pause the video and try to apply what we just learned about exponential functions to see if you can figure out how to do it without applying f and I and t. Pause the video. Okay, so if you gave this a shot, what we're seeing right here is that our rate of change let's pretend our function, let's call it oil, okay? If oil was equal to CE to the negative 0.2t, well then if we took the derivative of oil, in this case dO, we'll call it, or I'll just keep it oil, d-oil dt, well if we did this derivative, this would be negative 0.2 times C times e to the negative 0.2t. And doesn't that look a lot like this equation right here? So this equation for r of t that they gave us is an exponential growth model because we can see our original function is present inside that rate of change. So therefore all we got to do is basically just figure out what is that constant c. Okay, well that ends up being not too hard because we know that if d oil dt, this is going to be r of t, that function they gave us. We know that 0.2 times c must be 2,000. So that tells us that c is negative 10,000, okay? That's the initial amount of oil. So if we want to find how much oil we had, or what did it say, how much oil did we go through? How much oil leaks out of the tanker? What we're going to be looking for is the difference in oil between the times of 0 and the times of 10. And so recall that this value of C in our equation for our function for oil, that's the initial value, okay? So if we want a change, we're going to look at oil at the time 10 minus oil at the time 0, but oil at the time 0 is just that initial value. That's negative 10,000, so that's nice. So if we want to evaluate this, we know that oil is given by our function right here. So we can say this will be C, which is negative 10,000, e to the negative 0.2 times 10 minus 10,000. And if we do that, we end up getting the exact same answer, about 8,647. Now, in terms of a strategy, I would definitely say FNINT is way quicker to do this stuff, but I think this is a good problem to show you guys just because it illustrates how we can think about differential equations of a certain type as exponential growth equations now. We don't just have to be slaves to our calculator, which to be honest is just a black box. And there's a saying with black box things, and that's garbage in, garbage out. So what that means is that if you put garbage into a black box, it's going to spit you garbage back out. And if you don't know you're putting garbage in the first place, you have no idea the validity of the answer that you're getting back out of that black box. So if we think about it in terms of an exponential growth equation, that just makes sure we conceptually understand what's going on with this particular type of problem. But like I said, if you came into a problem that looked like this, either in one of my tests, a quiz, or an AP exam, feel free to just use FNINT. It'll be way, way faster. But now let's look at a problem that actually does require you to use your knowledge of exponential growth. All right, so pause the video, try to solve this problem. Okay, if you gave this one a try, notice that there's a very key phrase right in the first sentence of this problem, and that it's that the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. That statement right there is telling us that, let's say P is people infected, and people doesn't go P-O-E, it goes P-E-O. People infected. You know, maybe I should have written that down there in hindsight so you guys didn't have to waste 5 seconds of the video watching me write it, but I digress. Okay, anyway, if this is that, what that statement right there is saying is dP dt is equal to some constant times the current population. And that, as we know, is the differential equation for exponential growth. So that tells us that the population at any time is going to be an initial population, which they told us is 1,000, times e to our proportionality or our growth constant times t. So therefore, we know this will be 1,000 e to the kt. Now, it also tells us that after 7 days, 1,200 people are infected. So if we use that knowledge, we can say that, okay, well, that means 1,200 is equal to 1,000 e to the k times 7. Or we get 1.2 is equal to e to the k times 7. Now we want to solve for that value of k, because if we know that value of k, then we know the entire population equation for that population growth or decay. Yeah, and I know I've been saying these model population growth. I'm sorry, I completely forgot to mention that PERT also models decay, and it models decay when this growth constant k right here is a negative value. If that's a positive value, then it models growth. I apologize for not bringing that up earlier. But anyway, if we want to isolate this k right here, we can just take the natural log of both sides. So we'll get the natural log of 1.2 over 7 is equal to k. So therefore, if we want to go ahead and solve this problem outright, the problem asks us, what is the population 12 days after the what is the number of people infected 12 days after the epidemic is first discovered? So all we got to do is say, okay, well, P of 12 is going to be 1,000 e to the natural log of 1.2 over 7 times 12, and we have the entire equation. All we got to do is just plug and chug at this point, and if we do that, we'll get 1367. So we can come up here, and we know, therefore, that the number of infected people is given by the answer C. Okay, so in the next video, we're going to be talking about another differential equation that models growth, which is called the logistic differential equation, and it relates to growth in cases where we have limiting factors or where growth eventually settles on a particular population at a certain time. So I hope you'll join us.